Okay, this is lesson 7.3, and this is regular payments of an annuity. We're going to do this lesson in two videos. In the first video, I'm going to show you the two equations you need to be able to do the math for the rest of the unit and work through an example with each. And then on the back, we're going to use the equations that we develop in this lesson and work through an application question. So you have two options. You can watch this first video and try the back on your own, or you can watch this first video and instead of trying it on your own, you can work through it with me and watch the second video. Okay, so let's set up. For the first two lessons in this unit, you were introduced to two equations. The future value of an annuity, which looks like this, all over I, and the present value of an annuity that looks like this, no extra bracket. And in this video, what we're going to do is we're going to rearrange these equations and make them usable for our purposes to solve for R instead of A and PV. So why would we do that? Well, we could, if we know the future value or the present value of an annuity, we could solve for the payment. How much money do I need to deposit, or how much money can I withdraw? And it becomes a very useful tool. So we're going to work through two examples, and we're going to decide whether it's a future value or a present value equation. I'm going to give you the formula, and we're going to add that formula to our survival guides because it's an important equation. In fact, I believe I read it on the top of your test. So let's look at our first example. Example 1, determining payments given the amount. Well, that kind of spoils it. Brianne wants to save $6,000 for a trip that she plans to take in 5 years. What deposit should she make at the end of every 6 months into an account that earns 6% per year compounded semi-annually so that she has $6,000 in the future? And that's the key. We want to find the payment. Where does it say that? What regular deposit? We want to find R. Given that we want $6,000 in the future. We want to save $6,000. That's A. A is $6,000. So we need an equation that's set up to solve for R. And what I'm going to do, instead of us developing it, I'm just going to give it to you. R is equal to A times I divided by bracket 1 plus I to the exponent n minus 1 square bracket. And if you look at the original A equation, it's the same variables, it's just rearranged for R. So if we want to solve for R, we just use our new equation. This is the equation for payment given future value. And this should be added to your survival guide. Okay. In order to use it, we need A, which we have, 6,000. We need I, and we need N. So let's find I and N. I, interest, is 6% per year, compounded semi-annually. So semi-annual is 2 times per year. So to find I, we take our 6%, make it a decimal, and divide by 2, which gives us 0.03. Always the percent divided by whatever's after compounded. Now to find N, it's how many times she needs to make the deposit. Well, she's making a deposit twice per year for 5 years. So 5 years, 2 times a year, 10 total deposits. And now we have I, N, and A. We can use the equation and solve. So let's do it. R is equal to 6,000 times 0.03 divided by bracket 1 plus 0.03 to the exponent 10 minus 1, close bracket. Now this is the trickiest one to type directly in your calculator, but I'm pretty sure if you just type it in as it's written, even if you don't have a nice fractions button like I do on my calculator, it will still work out. So try typing it in your calculator and get practicing to try to get this answer. It's 16123 bracket 0.03. I'm going to make it as a fraction. Bracket, bracket, 1 plus 0.03, close bracket, exponent 10 minus 1, close bracket. And we get $523.38. So we can say Brianne should deposit $523.38 every 6 months. All right, let's try our second example. Example 2, determining payments given the present value. Donald borrows $1,200 from an electronics store to buy a computer. He'll repay the loan in equal monthly payments over 3 years, starting 1 month from now. He is charged an interest rate of 12.5% per year compounded monthly. How much is Donald's monthly payment? So how much does he have to pay back the amount he borrowed today? So to do that, we need a new equation. We need the payment given present value, which is R equals PVI over square bracket 1 minus round 1 plus I negative n exponent square bracket. This equation is our payment given present value. When figuring out which equation to use, always think about where's the money. Donald borrows $1,200. He's borrowing it now, and then he's going to pay back. Borrowing it now in the present, this is a present value question. The one we just did, Brianne wants to save $6,000 for a trip she plans to take in 5 years. 5 years from now, she needs the $6,000. Future value, this is a future value question. If you can figure out where the big amount of money is, it tells you which equation to use. So, back to our example 2. Donald borrows $1,200 from an electronics store. That's our PEV. So let's highlight that. That's our PV. To find I, we need an interest rate. Here's an interest rate, 12.5%. And we need to know how often it's compounded. Monthly. Monthly is 12 times. So, to find I, 12%, 12.5% is a decimal, divided by 12, because it's monthly. And we get a nice long decimal, which we need all of the decimals for. Because when you're working with exponents, things get really big really quickly, and we need as accurate a number as we can get. N, how many payments will Donald have to make? Well, he's repaying in monthly payments for 3 years. So 3 years times 12 times a year is 36 payments. So Don's going to make 36 payments. Let's find out how much. R equals PV, which is 1,200 times I. Yes, you have to write all the decimals. Over 1 minus 1 plus negative 36 square bracket. And if we type this one in our calculator, I'm not going to show my calculator this time. We get $40.14. Trickiest part to this one is you need to use that negative sign, not subtract for your exponent, negative 36. So Donald only has to pay back $40.14, but he's got to do it 36 times, so he's actually paying a lot more than $1,200. In fact, if you want to figure out how much more, you could say 40, 14, and he's doing 36 of those. So Donald is paying $1,445.04, which is an extra $245 for that computer. Okay, that's it for 7.3, part 1. And again, if you feel like you got a good handle on these equations, you can try part 2 on your own. If not, watch the part 2 video. Thanks for watching, and I'll see you next time.